In this video, I'm going to discuss electric potential energy of the two charge system. This system, let us say, there is a point charge Q fixed at this position. There is a point A at R1 distance from the charge Q and point B at R2 distance from the point charge Q. Now, let us take another point test charge Q naught, and as we know, if both are positive, then force acting on Q naught because of Q charge will be in this way. Because of that electric force, the Q naught will move away from point A to point B. That means electric force created by the charge Q is doing work done in moving the charge Q naught from point A to away. So how we can find the potential energy of this charge configuration? Let us say again, this Q naught charge is at a point A, which is at a distance R1 from this. First, let me write what will be the expression for the force on Q naught. The force, this is force acting on Q naught charge. This force will be, it's a Q naught upon 4 pi of epsilon naught R square, and this force will be along AB, this way, the force will be. Now, let us say at any instant, Q naught is at distance R from Q. Say here this is the charge Q naught, okay, at a distance R from this. Okay, let us define dW be the amount of work done. dW be the amount of work done in moving charge Q naught from distance R to R plus dr. Let us say this is R and R plus dr. So from here to here, in moving this Q naught charge from R distance to R plus dr distance, amount of work done is dW. So how we can write? We can write that dW would equals to, it's F dot dr. Since force is also in this way and displacement is also in this way, that means in this dot product, it is going to be F dr cos 0. Or we can write it's a Q naught over the 4 pi of epsilon naught R square into dr. Now, we know the relation between the potential energy and the work done. The two relation we write, it's a change in potential energy is equals to negative of work done. When we say this is work done by system. Work done by system, or I mean here is work done by internal force, you can say. And sometimes we also take du, that's a change in potential energy, is equals to work done. Here we take it's a work done by some external force or external agent. Here in this situation you can see this Q naught charge is repelled by the charge Q. That means force acting on the Q naught is Coulomb force because of created by the charge Q, and that is the system force. No external agent is moving this charge Q naught from point A to B. It's moving by the electric force by the charge Q. So here we'll write the change in potential energy, this is equals to negative of the work done, and we have written the work done expression from here. It's a negative of q naught over the 4 pi of epsilon naught r square dr. Let's integrate it. This is du to be equals to, it's a q naught over the 4 pi of epsilon naught, it's a dr over r square. Let us say dr over r square from the limit point A to B, and you can see the point A to B, it would be distance from R1 to R2. So here we put the limit for R, it will be from R1 to R2. This will come out to be, it's a UB minus UA, which is equals to minus of q naught over the 4 pi of epsilon naught. It's a minus 1 over r from r1 to r2. Or this minus will become positive. So you can write this is UB minus UA is going to be, it's a q naught over the 4 pi of epsilon naught. It's a 1 over R2 minus 1 over R1. Or in the more general way, we can write it's a UA minus UB to be equals to, it's a q naught over the 4 pi of epsilon naught 1 over R1 minus 1 over R2. So in this system, if you again see, this was the point charge Q, and this was the point A, and we are moving from Q naught charge from point A to B. This distance was R1 and this was R2. What we get is UA minus UB. This is potential energy between the point A and the point B. You can see the point A is near to the Q. This is equals to, it's a q naught upon the 4 pi of epsilon naught 1 over r1 minus 1 over r2. This is the important expression for potential energy of the two charge configuration. Now, if I say, if we take this point B to infinity, so you can write the change in potential energy between A point and the change between the infinity is going to be q naught over the 4 pi of epsilon naught 1 over r1 minus 1 over infinity, and potential energy at infinity will take it to be 0. We call it reference. Why we take this 0? Because of the charge point Q at infinite distance, its value is going to be 0. So what we get is the potential energy at a point A to be equals to just q naught upon the 4 pi of epsilon naught r1. If you just think of the, in gravitation system, what we get is, in gravitation here, if you take, this is earth of radius re, mass me, any mass m kept over the earth surface, the potential energy expression, if you remember, that comes out to be gmem upon re. Here, this negative sign indicates this mass is attracted to the gravity, attracted by this earth. The same way, if you take, let us say this is some big positive charge, and there is a negative charge, let us say minus q, and if we want to write what will be the expression, let's say if rb is radius, then its potential energy is going to be, it's a minus of 4 pi or 1 upon 4 pi of epsilon naught q naught upon the distance r. See, because this charge is negative, that's why we'll write the negative charge. That's why it's coming out to be negative. You can see here also the potential energy is coming out to be negative. Negative, it indicates was this negative charge minus q will be attracted by this charge capital Q. The same way as we get in the gravitation. So this is the potential energy of the two charge configuration. Of course, this potential energy is a scalar quantity, and of course its unit would be its joules. Now suppose if it is given more than two charges and we want to write the potential energy of this configuration. Say there is a charge q1, there is charge q2, there is one more charge q3. Okay, we want to write the potential energy of these three charges configuration, so we can write that potential energy will be 1 over 4 pi of epsilon naught. We have to write all the three combination, that is between q1 and q2. That's going to be q1 q2 upon, let us say distance between them is r12, plus it would be q1 q3 between q1 charge and q3 charge. Let's say distance between them is 13 r13, so it's r13 plus it's a q2 q3 over the distance between them, let us say it's a r23, it's a r23. So this will be the potential energy of the three charge configuration. Important thing is don't forget to write the sign. If it is both charges are positive, then of course this will be positive. If one charge is positive, other charge is negative, is going to be negative because its a potential energy is scalar quantity. Can you suggest what will be the total number of terms if we have four charge configuration? If there are four charges are given, say Q1, Q2, Q3 and Q4, how many terms we have to write then? Think over it. We'll discuss in the next session.